Hello, I'm Pau de Jorge and I will present our work, Reliability in Semantic Segmentation. Are we on the right track? Semantic segmentation is present at the core of many applications, such as self-driving cars that need reliable models. In recent years, especially with the increasing popularity of transformer models, we have seen many novel architectures. However, reliability metrics are often overlooked. In our study, we conduct a thorough analysis of recent segmentation models and compare them to older baselines. The core question in our study being, are state-of-the-art segmentation models improving in terms of reliability? The short answer is not in all metrics. We find that recent models do not have better uncertainty estimation and identify promising directions to mitigate that. For further details, see the full video. We focus on two key aspects of reliability: robustness and uncertainty estimation. In particular, we look at three different metrics for uncertainty estimation. Calibration, where we want the predictive probability of our model to match the frequency of correct samples. For instance, we would expect that on average, the predictions with probability of 0.9 are correct 90% of the time. Misclassification detection. In this case, we want to sort out the correct predictions from the incorrect ones. That is, we expect all correct predictions to have higher probability than incorrect ones. Finally, we look at out-of-distribution detection, where we want to identify samples that are outside of the training domain. For instance, an autonomous car in a snowed city that had not been trained on images with snow before. Drawing inspiration from the example of a self-driving car facing snow for the first time, we set up a benchmark by leveraging different driving datasets. All models are trained on cityscapes, which includes images of several European cities in good weather conditions. Then, we evaluate out-of-distribution performance by testing on IDD, which contains scenes taken in India, and ACDC, which captures scenes in more challenging conditions, such as nighttime, rain, or snow. We argue that there is an increasing domain shift from cityscapes to IDD to ACDC based on qualitative inspection and the performance of baseline models. Regarding architectures, our study comprises three different models from 5 different families. 3 of the recent families are transformer-based, but we also test the ComNext architecture, which is fully convolutional. As baselines, we use the ResNet backbone with 2 popular decoders, DeepLab v3+ and UpperNet. Here we show the MIOU error on the left versus the calibration error on the right. So in both cases, lower is better. We observe that as we increase the domain shift, all recent model families show a much milder increase in MIOU error compared to both ResNet baselines. However, when it comes to calibration error, all models follow a similar steep increase as they face domain shift. So our first takeaway is that all recent models are remarkably more robust, but they are not better calibrated. One of the most effective techniques to calibrate models is temperature scaling. In these plots, we show the calibration versus the MIOU error for each model. On the top row, we have the models prior to temperature scaling. First of all, taking into account both MIOU and calibration, we note that there is no single model that performs best in all scenarios. Moreover, although temperature scaling seems to improve calibration out of the main error is still significantly higher. This begs the question, is there any way to improve calibration out of the main? In that regard, we explore 2 different methods that perform content-dependent temperature scaling. The first one consists in clustering the calibration domain into different subdomains. Then, a temperature is computed for each cluster, and at test time, we apply the temperature of the closest cluster. The second method trains a small network that directly predicts the temperature map, with an individual temperature per pixel. It does so based on the input image and the corresponding segmentation logits. Quite remarkably, we observe that even if the calibration network, depicted in green, only sees cityscapes images during training, it is able to significantly improve the calibration error, especially under strong domain shifts, that is, for ACDC dataset. On the other hand, cluster-based temperature scaling is usually not much better than vanilla temperature scaling. For a more in-depth study, please refer to our paper. For in-distribution samples, temperature scaling performs best, which could be due to the fact that cityscape is a fairly homogeneous dataset. Regarding misclassification detection, interestingly, we observe that ResNet baselines seem to perform best in distribution. However, out of distribution, the trend changes, and we observe recent models perform better. For out of distribution detection, we observe an inverse correlation with the MIOU. Indeed, when it comes only to auto-distribution detection capabilities, a small ResNet 18 is the best architecture. Finally, we study how model calibration can improve other uncertainty metrics. We find that using a calibration network can improve misclassification detection quite notably under strong domain shifts. We also observe some improvement when it comes to auto-distribution detection, albeit milder. To sum up, we have seen that although recent models show remarkable improvements in robustness, they do not translate to calibration out of domain. In that regard, there is no single model that performs best in all scenarios, but we identify a calibration network can help. When it comes to misclassification, ResNet performs best in domain, but recent models are stronger out of domain. And we also observe that better performing models in terms of MIOU tend to have worse auto-distribution detection. Finally, we also find that improving calibration can also help improve other uncertainty metrics as well.